Hello everyone. Let's look at question number 1 from the 2016 AP Calculus free response. This is a calculator allowed question. It is also a rate in, rate out problem. As I read the question, I will be underlining some key important information that we're going to use later on in A, B, C, and D. So water is being pumped into a tank at a rate modeled by W of T. You should label this rate in. And the units here are liters per hour. T is greater than or equal to 0 and less than or equal to 8. Now, right away, you should take this function and store it into y1 so that later on, you don't have to type this out again when you're using this function. T is measured in hours. Water is being removed from the tank at a rate modeled by R of T, liters per hour. R of T is not given to us in this question. However, if you look into the table above, we have specific values of R of T for different hours. So R of T is the rate out, and R of T is also differentiable and decreasing. If you see the word differentiable, you should be making a mental note to yourself that R is also going to be continuous. Any function that is differentiable is also continuous. Here, R of T is decreasing as well on the interval from 0 to 8. Selected values of R of T are shown in the table above. At time t is equal to 0, there are 5,000 liters of water in the tank. Here, this is your initial amount. You always want to label the initial amount so that you don't forget about it in other parts later on in the question. Part A, estimate R prime of 2. Whenever you see R prime, the reaction is let's derive, plug in the 2. However, there is no function for R of T in this question, so we're going to have to estimate it by using the average rate of change. And what we do is find two values of T that are closest to 2 and sandwiching 2 from the table. And we have 1 and 3 here. Use the approximation symbol. And let's look at the difference between the two rates, the rate at 3 and the rate at 1. That will be your numerator. And divide the change in time. The rate at 3 is going to be 950 minus the rate at 1, which is 1,190. You don't even need a calculator for this portion. The answer is going to be negative 120. Indicate units of measure. Because we're talking about a change of a change, or in other words, the change of a rate of change, the units it's going to be liters per hour, or you can write it as liters per hour squared. And that is all for letter A. Moving on to letter B, it says use a left Riemann sum, think rectangles now, with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. If you see the term total amount, immediately in your head you should be thinking of the integral. During 8 hours, the integral is starting from 0 and going up to 8. Inside, we need to find the function that represents the rate at which the water is being removed, and that is R of T. So start with this setup, and we're going to estimate it by using a left Riemann sum. Think rectangles. What I like to do is actually go to the table and find the differences between the T values. So the difference between 0 and 1 is 1, between 1 and 3 is 2, and between 3 and 6 is 3, and so on and so forth. Now, these are going to be the widths of your rectangles. So you want to take each width, starting with the first one, and multiply it to the leftmost height. Now, the height of your rectangles are going to be the R of T values. So the first height we have 1,340, plus the next width is 2, and your next height would be the 1,190. Keep going, a width of 3 times 950 plus a width of 2 times the height of 740. And again, you're thinking rectangles here. Now notice the last height we're not going to use because we're finding a left Riemann sum and not a right Riemann sum. Is this an overestimate or an underestimate of the total amount of water removed, and give a reason for your answer. Here is where a picture is worth 1,000 words. Draw yourself the scenario here. Go back to the question, find R of t, and see if that function is decreasing or increasing. And if you were diligent with underlining key information, then you would have noticed that R of t is decreasing on this interval between 0 and 8. So go ahead, draw yourself a decreasing function, and what you're going to do is draw rectangles where the left side or the left height is hitting the curve. And when you do so, you're going to see that the rectangles come a little bit over the curve. In other words, the area of the rectangles are going to be greater than the area under the curve. Hence, this is an overestimate, or your answer is an overestimate, because, and the reasoning is simple, because R of t is decreasing, and also we're using a left Riemann sum, or a left Riemann sum is used. And that is all for letter B. Moving on to letter C, use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. When you see the word total amount, again, you should be thinking integrals. And because we're looking for the total amount at the end of a time period, you need to remember 3 things. The setup is initial amount plus the integral of the rate in minus the integral of the rate out. In the context of this problem, the initial amount, hopefully you underlined this already, is 50,000 liters plus the integral from 0 to 8. The rate in is represented by W of t dt, and the rate out is from 0 to 8, represented with R of t, and we close it off with dt. Notice that this last integral here, we already found the answer to this from part B, where we found an estimate of this answer, which is 8,050. W is defined, so as long as you have this stored into Y1, your calculator should be able to do the work when you hit Math 9. And here is the setup on the calculator. The answer that you're going to get is approximately 49,786 rounded to the nearest liter. On the free response, again, you're going to have a lot of space, and oftentimes the setup is very simple. The calculator will do the work for you, so there's really not much that you have to write here. Now, letter D. Letter D is a very interesting problem. For t is greater than or equal to 0, and t is less than or equal to 8. Is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? The word same in math, you should be thinking equals. So what we're really looking for here is there a time during this time interval 0 to 8 where the rate at which water is being removed is equal to the rate at which water is being added? Another way to write this is to get their difference, right, where the difference between the two rates is equal to 0. We know a few things already. The rate W of t is an exponential function, and therefore W of t is continuous. We also know that R of t is continuous because R of t is differentiable. And because we're dealing with two continuous functions, their difference, the function W of t minus R of t, will also be continuous. So we want to look at what's happening to the difference of the two rates at the beginning of this time period at t is equal to 0, and what's happening to those two rates at the ends of this time period. by evaluating both rates at 0 and finding their difference. So W of 0 minus R of 0, the difference here is going to be 660, which is greater than 0. And the difference of the two rates at the end of the period is a negative 618, which is less than 0. Interestingly, the signs change from the beginning of the time period to the end of the time period. Here is where we can use the intermediate value theorem. By the intermediate value theorem, and you can also write IVT, by the intermediate value theorem, there exists, this theorem guarantees that, there exists a value t where t is between 0 and 8, such that W of t, the difference of your two rates, minus R of t is equal to 0. In other words, because the signs change, we're going to, and because these two functions are continuous, at some point the difference will be 0. And of course, this implies that at some point W of t will be equal to R of t. So there is a time where the two rates are the same. And this is the end of question 1.